Hello. Thank you for coming. 5:20 p.m. on a Sunday on day 3 of a festival. Hopefully we still have some brain cells, but if not, you can just look at the pictures and they'll be fine. So I love a long talk title. So we're going to talk about flexible PCBs, and specifically we're going to talk about things I've learned from sort of DIYing scrappy flexible PCBs with different people. So first, who am I? I struggle to find a noun for myself. I sometimes say researcher, sometimes maker, sometimes educator, sometimes none of those things. And I mostly work with electronic textiles, so e-textiles, and with flexible electronics. And these are some projects I've worked on in the past. I have worked in makerspaces and fab labs. So the top is kind of workshops I've done as an educator. The middle is more close to projects we'll talk about today on flexible electronics, so some flexible LED circuits. And then on the right is a raincoat that makes sound. Sound, not music. If you like screechy synthesizer sounds when you're walking around in the rain, you might want to make this. I also have an interest in combining electronics and modern technology with heritage crafts, like textiles. So I've recently learned about passementerie, which is the art of making trimmings, and been doing some work on combining them with textiles. But we're not talking about it today. And for work in my day job, and my job is also paying for me to come here, so thank you to my university. I'm a lecturer in an engineering department, the engineering department in Nottingham-Trent University. So if you're not from the UK, that's about 3 hours north of here. Nottingham's famous for Robin Hood and pretty much nothing else, unless you're a textile history nerd and you're like, oh my god, the historical home of lace making. But I didn't see anyone jump out of their seats thinking of that, so you probably haven't. That might be a new fact for you. So, let's start off by defining what flexible electronics means, because you might have some idea of what it is, or you might be like, I don't know what that is at all. So, when we talk about flexible electronics, you might think that's any electronic device that can bend. Conventionally, that's not exactly what it means. So we're normally talking about a polymer film, a plastic film, that's got metallic tracks on top, like you would have in a regular PCB. And you normally also have components or connectors, and these are either going to be soldered or crimped on top of that. So basically, it's a conventional PCB, but bendy. So instead of being on rigid FR4, which is the normal material our PCBs are made on, it's made out of a flexible plastic base. So it doesn't normally include things like e-textiles, which are made on fabric. And for shorthand, we will say flex PCBs. Save me one syllable. A bit of a note on terminology. I'm not going to be super precise about the use of the terms PCB, flexible electronics, etc. There are people who have very strong feelings about whether something is a flexible PCB or a flexible cable. Normally, I'm in favor of being pedantic, but I don't feel like today is the time for that. We don't want to spend half an hour doing definitions. If this upsets you, please remember that the P in PCB stands for printed, and most PCBs aren't actually printed, so you can be upset about that instead. So language is complicated. I'm not the problem here. Don't come for me after in the Q&A tent about my use of terminology. So to go back to those pictures I included on the previous slide, you might think, you might know what we use flexible electronics for, or you might think, like, why would I want that? So applications can include cameras. So inside digital cameras, if you've ever opened one on purpose or by accident, you might have seen these amber-colored, flexible, kind of thin PCBs bending around corners or connecting one circuit board to another. So they're basically really useful for saving space. These aren't bending constantly, but they're kind of bending into a compact form or going around a corner and saving space where you might need wires instead. So you'll save space and weight by using a flexible cable or PCB instead of a wire. Similarly, inside a smartphone, a scale bar would have been great for this image, but this is a little camera module from a smartphone that's probably only a couple of millimeters wide, and we've got a tiny little flexible cable connecting the actual camera component to what's probably a connector I didn't check. So this is going to need to be mounted on top of another PCB inside the camera, so to save space to do that, you can use this really, really tiny cable, which has loads of tracks in a tiny space. You can also use flexible PCBs in e-textiles. So this is from a teardown that Adafruit did of a shirt called the Twirkle shirt by Cute Circuit, the e-textile brand based in London. This shirt lights up as you move, And it's basically got these long strips of flexible PCB along which there are islands with a little LED and 3 resistors. And these are sandwiched between layers of fabric in the garment. So instead of using conductive threads or textiles, which might be familiar to you if you do e-textiles, you can use flexible PCBs instead. Finally, here's a sensor array for robotic skin. So we might want to have an array of sensors or other components for a robot which needs to bend and flex, and we don't want that to be a huge rigid island. Or you can use it for art purposes, and I haven't included an art example, but you can just use your imagination for that. So just to summarize that, when we say flexible electronics, we're talking about electronic devices on flexible plastic films to fold into small spaces or enable electronic devices to bend and flex. The bending and flex part is of most interest to me as someone with a background in e-textiles. So then what's this talk about? Are we done? Like, we've defined flexible electronics. Can we go on to the next thing? It's not a hardcore flexible electronics engineering talk. What I would say is, like, I used this meme in a lecture with my students this year, and I realized all of them are too young to have seen this film when it came out, but I don't care, because they need to be educated. So our community, the EMF community, the broader hacker maker community, we make a lot of PCBs. Some of these were designing and having manufactured, and some of these were like engraving or etching in our hackerspaces or makerspaces. But I don't see a lot of evidence of flexible PCBs being made. Some people are, getting them made and using them in projects, but I don't see a lot of them. I will say I haven't obviously been around every makerspace, but I do think this statement is largely true. We're not making them, and I think this should change, because I think the more we're able to make our devices ourselves, the more we can democratize technology, and then the more people who are non-experts in electronics can also make things themselves, and that's always a good thing. So then, to understand why this is happening, how to address it, we're not done with this meme. I should have also, I had the source link, I think, in the original slide, and so if you've never seen this, you might be confused, but that's okay. We need to understand what the barriers are. So what are the things that are stopping us from making flex PCBs? And then what tools and materials and documentation do we need to change that? So this talk is just kind of a reflection on early stage work I've done on this, some workshops I've done, my own personal experiences. It's not a peer-reviewed study. I did try and pitch to my university ethics committee that I embed a study in a workshop, and they were horrified by the idea that people would be using machines. So we need to work a bit more on that before I can do that. But yeah, that's the basic idea. So my personal motivation for this, how did this start? So I did a PhD in flexible and stretchable electronics for e-textiles, and I made a lot of flexible PCBs for this. I don't think this video is going to play by itself. So this is a stretchable structure that's made out of a thin strip of flexible circuit with some very small LEDs on it. That by itself was flexible, but if you bend that into a helix, because of the geometry, it's now stretchable. But then to make this device on the top, which is 2 millimeters in diameter, I had to make a flexible circuit on the bottom left, which is only, I'm doing this like it's to scale, it's not, 1.5 millimeters wide, and has tracks on it that are only 0.1 millimeters wide. And you might say, okay, why struggle and make this yourself? Why not get it manufactured? The benefit of being able to make it myself was that I could test and iterate lots of different designs instead of having to wait and try, do that. So what was my next point? So I found the conventional fabrication methods, because I did test these, a bit tedious when you're a researcher working in a lab that's not like doing this all the time, when you're not doing these things kind of every day at high volume. And because I've worked in makerspaces and hackerspaces, I was constantly thinking, like, this would be such a cool thing to do in these spaces, but these methods just don't really suit. So then I started to think, can we DIY our own PCBs, flex PCBs, using equipment that we would find in a fab lab? So before we talk about how to make a flex PCB, we should look at what the parts are. So we have a substrate, that's our base layer. In a rigid PCB, this would be FR4, and in a flexible PCB, this is usually polyamide. Not to be confused with polyamide, which is nylon, just to make these things confusing. It's usually known by the brand name Kapton. You might have come across Kapton tape in electronics or in 3D printing. So it's this amber-colored tape that's nice because it's heat resistant. And it's the base layer for any of these amber-colored PCBs, flex PCBs, that you'll see inside a device that you've seen the inside of for whatever reason. On top of this substrate, we have our conductive tracks or traces, like we'd have on any PCB. Normally, these are made from copper, but not always. And then, similar to how you have a solder mask in a conventional PCB, you have something called a coverlay. This is usually a piece of capped-on film that's laminated on top, with openings for components to be soldered. So in a rigid PCB, this is basically like insulating your traces, but in a flexible PCB, it's also providing some mechanical support, because the most delicate part is these bendable copper traces, so this coverlay helps them not to crack. And this is a terrible picture, actually, but this is actually a little temperature sensor flex PCB I made for a temperature sensing garment. So we have some components on the top as well. Almost always surface mount. You rarely try and do through-hole components with a flexible PCB. If you want to, you can. And then you also have encapsulation. So this we see less often in conventional PCBs. This is adhesive or some other material that goes on top of your components to help them not break off, basically. Because anytime we have a boundary between a rigid material and a flexible material, you get a concentration of mechanical stress, and you can end up with cracks or breaks there. So if you add this encapsulation on top, it helps allow your PCB to actually bend. Unless your components breaking off is what you want, like some kind of one-time performance art, in which case I support you to do that. So then, how do we make these conductive traces or tracks? Well, we can use printing processes. So on the left, we have screen printing. Screen printing has been around for centuries. We have a mesh with some openings in it to let ink or whatever we're printing through. So we can print silver ink. On the right is a Volterra V1 dispenser printer. So this is a cartridge of silver ink that's printing a design on a piece of Kapton. So we can print with silver ink. The issue with both of these is that the silver ink's very expensive. Like 5 cc's in that cartridge costs about 90 quid. It has a shelf life, and it's nice, and they're really nice to look at, and they look impressive, but actually to do some quick prototyping, they're not my favorite. What's really common in PCB manufacturing is etching, or photolithography is the term for the most common way to do this. So in this case, we have Kapton film, our flexible polymer film. It has some really thin copper sheet. When I say thin, really thin, I mean like 20 microns, so 20 thousandths of a meter, laminated on top of it. And then we create an etch mask or an etch resist, so the pattern of the circuit we want to make. We pop that in an etch tank, which is a chemical that's going to eat away any unexposed copper. You can see that process kind of happening here. And then at the end, we clean off that resist, and we're left just with the traces of our circuit. So some of you may have used this. This is something you can DIY, but it uses some pretty nasty chemicals. We did have an incident in a lab where I used to work where someone was etching late at night, and I came in and the whole floor was orange because ferric chloride is leaked all over the floor. So that is a downside of late night PCB fabrication, but no one was harmed. I just got really angry. So if these are the two main issues for methods for creating these conductive tracks, what are my problems with them? So the materials I've mentioned are expensive. So polyimide Kapton is expensive. I think if you want to buy like 6 A4 size sheets of polyimide film, you're talking about like 50 quid, which is not great. And then if you want the copper-plated polyimide, you're talking about like 20 times the cost of just copper-plated FR4. So the cost of going from a rigid to a flexible PCB that you're making yourself can really get exponentially high. The methods can be quite tedious, so this etching method, the professional way to do it involves like getting a UV-sensitive film and laminating it and exposing it to UV selectively and then developing it and waiting and we won't go through all that. It made me really annoyed a lot of times, so it was like, I need something faster. And these work really well in an industrial setting, obviously, where all your equipment is calibrated and it's being used every day, and you're churning out a lot of these. But if you're an individual researcher or you're a maker in a makerspace or you're not doing this every day, we need something that works a bit better. There are also DIY kits for etching PCBs, but they're not available everywhere. The companies that make them seem to kind of go out of business and then pop up again. And most of them require that you have a laminator, because they're like, everybody's got a laminator. Everybody doesn't have a laminator. And then etching PCBs, I kind of already gave the example of the orange stained lab, but they can be messy. I've bleached my clothes by accident several times, even wearing a lab coat by working with those etching chemicals. And you're either kind of working with a tray with this hazardous chemical in it, or you have to buy an etch tank. And if you want a good one, they're quite expensive. So when I say I'm trying to make flexible PCBs DIY, what we're focusing on is an easier and/or cheaper way to make these conductive tracks on a flexible substrate. Also, maybe a cheaper and more widely available substrate material. And then the target users are kind of people who have access to the kind of machines you would find in a makerspace. And then another goal is, in theory, for younger makers to minimize the use of hazardous chemicals. But I also don't love the anxiety of wondering, like, did I wash my hands? Have I stored that correctly? Is that going to blow up in that container? So if you can rule those out, I also have a bit less anxiety for me. Worth mentioning as well, there's some new methods that might make their way into makerspaces in the future. So this is the FiberQuid project. I recommend looking this up if you haven't heard of it. So you can't laser cut copper with a normal CO2 laser because it's too reflective. But if you use a fiber laser, which is higher power, you can do it. So you can engrave circuits in the same material, copper-plated Kapton. Or if you have a laser cutter, you can basically burn carbon tracks into Kapton, and then you can electroplate that if you have an electroplating setup. So these are two nice methods, but I would say neither of them is super highly accessible because you either need a fiber laser or you need a electroplating setup, which loses marks for me for using hazardous chemicals again. We can't avoid using all chemicals, but I'd like to minimize the nasty ones. But these are two nice methods. If you want to know more about the fabrication methods, I did write a paper on this. I should link that on my website or something as well, because I'm probably going to move on too fast for anyone to scan it. So at the Fab25 conference last year, which is kind of the international meeting of Fab Labs, I should say a Fab Lab is a new word for you. It's basically like a subset of makerspaces that kind of have a certain inventory and are in a network together. So yeah, I wrote a paper on that, which is open access and hopefully not the most obtuse paper that you've seen. So okay, so you've said maybe you're like, okay, I want to make a flex PCB. How do I do it? So I'm going the wrong way. You could design one and have it manufactured, but that's not what we're talking about today. And then there are DIY etching methods. So, but you still require like an etch tank and the copper-clad Kapton, which is expensive, and you need etching chemicals. These are some methods you can use for that. So you can actually draw your resist, your circuit pattern on with a pen. There are kits which allow you to print on special paper that you laminate onto your material, and it transfers the toner, which becomes your resist. Or you can also use a vinyl cutter to make a sticker, which is my personal favorite method. And these are all covered in that paper on the previous slide. Some people have etched PCBs with salt and vinegar, which is less hazardous, but it seems to take about like more than 12 hours. And they're like, you can speed it up with hydrogen peroxide. And then again, we're getting into dodgy territory. So that's, again, not super what I want. Yeah. And then again, we're still using a substrate material that's quite expensive and not available from many suppliers unless you're kind of a professional. So this is my preferred method. I will say it's not my totally original idea. I'm just kind of trying to tweak it a bit. So copper tape is thin copper sheet on an adhesive backing that you can get in many hardware and gardening shops because apparently slugs hate it. I don't know if slugs hate it, but sure. If it's being sold in shops and anyone can go in and buy it, I'm happy to support the propaganda that slugs don't like copper. It's used a lot in paper circuits, which you might have heard of, popularized by G-Chi and the company Chibitronics. So they use narrow copper tape to kind of map out simple circuits. But you can also push things a bit further and use a vinyl cutter. So there have been a few vinyl cutter workshops this weekend. If you haven't heard of one, it's basically a computer-controlled knife, normally used to cut like graphics for T-shirts or stickers or various crafty things, but you can also cut some flexible PCBs as well. I realize I've shown 2 videos where we're not making anything that looks particularly PCB-ish, but you can take my word for it. So that is my preferred method. This is a bit on the process. We're not going to go super in detail into this, but just to give you an overview. So first you make your design. You can use a PCB design software like KiCad. But if you don't know how to do that, or you're just not bothered opening it, I'm not saying I've not been, that's happened to me. I'm like, I can't be bothered making a proper PCB layout. You can also just draw it if it's a simple circuit in a design software like Inkscape or Illustrator. Then you have to make it cuttable. This means putting it into a format that your vinyl cutter wants, and this is very dependent on the machine. They all have their own preferences. And then there's two things you can do. You can stick your copper tape on your substrate, and then if your machine allows you to cut at different forces, kind of in the same go, you can cut the copper tape just by itself, peel off the rest, and then cut your outline, which is quite nice, but it does have some downsides as well. Or you can cut them separately and stick them together, which is what I was doing on the right-hand side here. So we start with a piece of copper tape that you might be able to see has a pattern cut out of it. You peel off the bit that you don't need. Then we stick some masking tape on top so we can transfer that to our base material, and you're left with some copper tracks on, in this case, this is PU polyurethane, I think, the kind of like squeaky material that raincoats are made out of sometimes. If you're using coverlay, the kind of insulating film, you can use that at that point, then solder your components, and then you can apply encapsulation to protect the components. But you can skip these. It just means that your PCB will break more easily. But in practice in workshops, I haven't been using these that much, because we're just kind of trying to get the basic idea across. You might be thinking, like, OK, well, this isn't Kapton, so can we use cheaper base materials? Kapton polyamide has many advantages. High heat resistance. You can solder to it, and it's not going to melt. It's got good strength. It has other things I can't think of at the moment. And it is definitely the standard, but it's expensive and it's not very sustainable. It's not biodegradable. And the company who make it don't have the best environmental track record. So lots of other plastics, flexible plastic films, but then the question is, will soldering melt them? And I'm going to leave that as an open question for now. And then what about sustainable substrates like bioplastics, mycelium? If you know anything about biomaterials, you might think, well, can we use those in flex PCBs? So what I've been doing so far is to figure out, like, OK, I think this is a nice method. I've made lots of little flex PCBs. I think it's fun. Do other people agree with me? They might not. So I've run 5 workshops so far, and we're going to briefly look at them. Each have been with different people, mostly in different countries, and I've learned a lot from them. And on the right-hand side, the images are kind of what we've made in these workshops. So you'll notice maybe all of these are very simple LED circuits. So the one in the bottom middle is literally just an LED and a battery. This is a prototype. I did put in a current limiting resistor later if anyone's like, that's bad practice. And then all of the rest of them are just like a parallel LED circuit, but they've been designed in a way to make them look visually appealing, because some of these were with people who don't have much experience in electronics, so we want to do a simple workshop, but looks kind of fun. And also to show, like, just making like 2 lines with some LEDs on it, that's not very exciting. But if you can do something a bit more creative, it's more fun. So that's my view anyway. And I've said this already, so each workshop was a little bit different, so I kind of iterated through different things as we went along. First workshop was at the Fab 25 conference last year. So we did the method where I kind of applied the copper tape to Kapton first, and then tried to cut it, and then peel the excess copper off the Kapton. This ended up being really fiddly, partly because I realized, oh no, I don't have enough like tweezers for weeding the copper tape for a whole workshop group, so I better buy a load of tweezers, and they were terrible. So there was a lot of like, noises as people struggled with this. And then I thought, like, we'll go through the whole process. These are makers. They want to see how to do this on the vinyl cutter. But then we were, like, all queued at the vinyl cutter, and it didn't work very well. So someone was like, hey, we run vinyl cutter workshops, and we kind of do a bit of, here's what I made earlier. But people did get their circuits working. This man in the top right is a nice German man called Michael, who's like, I will help teach people how to surface mount solder. So very grateful to him. I also learned that many people feared the vinyl cutter. They're like, we have one, but I don't like it. And I still haven't fully gotten to the bottom of this, but it seems to have a reputation as a machine that's a bit fiddly. And in some fab labs, it seems to be just pushed to the side, gathering dust, and people are like, that's too fiddly for me. Which I find sad, because I'm a big vinyl cutter fan. So I'm hoping maybe we can rehabilitate the image of the vinyl cutter. Second workshop was about a month later in Center Rog, which is a wonderful community manufacturing hub in Slovenia. They have all kinds of different labs in a big old factory. And this time I learned, well, cut the parts in advance with a couple of like pre-designed circuits, and then people can just see how the vinyl cutter works. So that worked better. And these are members of the public. Most of them had never soldered before, and all of them managed to get the hang of surface mount soldering within a few minutes. One woman was like, I'm actually, like, I just got my eyes tested and I need glasses real bad, and I can't even see the components, but between the two of us we managed. And we did use some clear nail polish as encapsulation, which is a trick from e-textile people. Clear nail polish can be used to seal things in e-textiles. And we didn't use any cover lay, but then part of the reason for that was in a workshop, sometimes you want to tailor for different skill levels. So I wanted to be like, OK, you can put the LEDs anywhere. If you want to just put one on somewhere that looks nice to you, that's fine. Or if you want to go nuts, like the guy on the left, that's too many LEDs. That's not going to be super flexible, but he liked it, so that was fine. So that was that one. At PIF Camp, which is an art and electronics summer camp, also in Slovenia, I decided to experiment with cheaper materials, so get rid of the Kapton because it's expensive, and instead bought these PET sheets in different colors. And this is just a simple LED circuit, so soldering a battery, an LED, and a resistor. And we found that you could solder these, but you had to be pretty fast, otherwise the PET was melting under you. So to kind of help with this, I had people do sort of practice soldering, so just practice on some scrap bits of copper. So if they hadn't soldered before, which some of them hadn't, they could get a feel for it instead of like soldering and then everything's melting away. So everybody did make a working LED circuit, and so that was like interesting. I mean, our flexible DIY PCBs don't need to look super professional. If they work, they don't need to be as robust as ones that are professionally made. So it's good to know that you can kind of use cheaper materials. Then a few months ago, I did another workshop at the Open Hardware Summit and realized that all of the ones I'd done before don't really use the flexibility of the circuit. They're just flat. So they could have been a rigid PCB. So for this one, again, I pre-made the parts, and you could choose whether you want Kapton PET, which is clear at the top, or polyurethane. And this was a simple add-on or shitty add-on for the conference badge. So it sticks onto the badge that you got when you registered. And in this case, you could fold it into a loop, or you could make a Mobius strip, which if you're a fan of non-orientable surfaces, maybe that's exciting to you. And this for me is Gorilla Epoxy, which is a nice epoxy you can buy in hardware shops to use as the encapsulation. And I didn't figure out how to do the cover lay well, but we did use some Kapton tape to kind of help with the soldering, help up the solder to not go everywhere. So again, kind of learning things as we go along. And again, no one melted their polyurethane, so that was good. And then the final workshop was a bit of an outlier, but I thought I just included anyway. So this was at the New Interfaces for Musical Expression conference in London a couple of months ago. And this was, we're not making an LED circuit, there's no soldering, but participants were making a moisture sensor that then is a pitch controller for a simple synthesizer circuit that we built on a breadboard on the far left, which goes into this kind of like rain cloud thing. And then that goes on the inside of a raincoat, and you put the moisture sensor on the outside. This does have some sound, so we're going to try. It's going to be quite screechy, so we'll see what happens. He's being silenced. Okay, we might skip to the next one. This one's quite nice. I like this one. So quite a fun sound from a simple circuit. And then this was the one kind of functional. Beautiful music. So kind of not the same as the other workshops, but still getting used to like using the flexible material, and the copper tape. So that's kind of what I've done so far. Ongoing issues are aligning the copper tape with the substrate can be a bit fiddly. A vinyl cutter software usually isn't great, and different vinyl cutters have completely different software. So it's like you need to learn each one's quirks. So far I've used these 4 different vinyl cutters, done it successfully with all of them, but have had to spend time like getting to know each one. And then some machines, like Cricut machines, are very, very common, and they're quite... I have a mini one, which is my travel vinyl cutter, which cost me like 150 quid, and I think that's great, like, affordable piece of machinery. But the software is always like, hey, you don't want to change that setting, it's fine. Or, no, I think you're doing that wrong. And it's always trying to sell you stuff. It's like, you should buy these patterns. I'm like, I don't want that, thank you very much. So, yeah, that's kind of annoying. So these are all things that might be a little bit off-putting for people. And then I haven't yet attempted to make the coverlay part in a workshop, so that's kind of unsolved. Bonus project, I mentioned flexible substrates earlier, so I did have a collaboration with my friend and collaborator Marisa Satcha at PIF Camp again last year. So Marisa's she works with bioplastics a lot, so plastics as you kind of cook out of sustainable materials. So these are some gelatin bioplastic films that we made, and then we made a touch sensor array and a really quiet speaker that you had to lean really close to listen to, because neither of us is an audio electronics engineer. And these did kind of work. We had some issues with adhesion and some fun issues with humidity, because bioplastics love to go crazy with humidity. But it was kind of promising, and we might do a bit more on that if it ever makes it high enough on my to-do list. So we're almost out of time, but in the future I would like to do a more structured study to kind of identify what are the tricky parts of what works and what doesn't. Also, like a low temperature bonding method so we didn't have to solder would be better. There are conductive adhesives, but these are also kind of pricey, and they can take a day to set, which isn't great if you're trying to do quick prototyping. A non-painful and inexpensive way to make coverlay film would be great. And then more investigation into like biodegradable substrates. I didn't do a workshop or suggest one because I'm tired. I've done too many workshops, but I would like to do more in future. So if you're like, I would like to participate in that, or could potentially do a distributed online workshop, it would be good to know if people are interested in that. And then documentation. So on that subject, I'm behind on documenting most of what I've learned, but this presentation is on my website if you want to look at that. And I do feel I have a little bit more work to be done before I can make proper documentation, because I started documenting it after my first workshop, and then I was like, within a month I disagreed with everything I'd said. So a bit more to do. Thank you for listening to me. This is where you can contact me, and this is a picture my niece drew of me and her going on an adventure. So I'd like to include her art in my talks. So yeah, thank you for listening.